As I mentioned in the last video, my next step was to get the amplifier on a PCB and put some heat sinking around those BS170s. So I've started to do that. Here's the circuit in kicad, and it's basically a direct copy of the one I had in LTSpice earlier. So here's the kind of the two-stage input here. And I really should have some kind of 50 ohm impedance matching on the input, which I don't have at the moment, but I probably will do in a later rev of this. So there's the two-stage amplifier on the input, the 2N3904 and the 2SC5706. And I'm actually going to do both of those as SMD versions. So if we just swap to the PCB here and scroll out a little bit. So this is the PCB right here, and here's those two stages on the input here. This is the 2N3904, and then over to the right we have the 2SC5706. So that's basically what I'm going to do on the circuit itself. Let's just go back to the circuit pretty quickly. These two splitters here are the exact same splitters that the exact same toroids that I had in the on the previous PCB. So they're the binocular toroids. The BS170s, they're both the TO92 package. I actually do have some surface mount BS170s, and they are rated the same, but I wasn't quite sure how to properly heat sink them. So I might play around with that a bit more. So anyway, let's move on to the circuit itself. I've started to build it up, and I can show you what I'm up to. Right, so here's the PCB here, and so this is the input here. Here's the output here. This is where the low-pass filter goes. Here's the power supply circuitry here, and that's the 5-volt regulator. I've got one of these PCB mount barrel jack inputs right here. And then here's where the 2N3904 goes right here, and the 2SC5706. So I've built this portion up. So what I'll first do is check and make sure I'm getting 5 volts out of this regulator, make sure I'm getting 12 volt through to here. So I'll do that right now. Okay, so I've got the power supply connected now. So basically I'm doing this around the camera. So I should see 12 volts right here. And close enough, 11 volts. And then this is the 5-volt regulator here. The input is on the top side here. The output is on the bottom side. So let's probe down here. And there's 5 volts on the output. So that shows that that's all wired up correctly. I haven't got any shorts, and I've got the regulator the right way around. So what I might move on to next is the input side here. I'll get the 2N3904 installed, and then we can test to make sure that this part's installed correctly. Then I'll move on to the second stage, and then it'll be the BS170s and the RF splitter and combiners. So that's coming right up. Okay, so I've installed the first stage, as you can see right here. So here's the bias resistor divider on input, the 4.7K resistor, 1K resistor. Here's the 2N3904, and then here's the two emitter resistors here and the associated capacitor with it as well. And then this is the transformer on the output that has a 24 turns to 7 turns winding ratio. So it's 24 turns on this side and 7 turns on this side. And then finally, to simulate the output of the second stage, I've got a 43 ohm resistor here, and I'm tapping off the result there. So I thought it'd be worth going and calculating the input impedance of that stage. So for a transistor configured with a resistor divider on the bias and an emitter resistor, this is the formula right here. So it's R1 in parallel with R2, where R1 and R2 are the resistors forming the bias divider. And then that's in parallel with beta AC outside of VT on IEQ, which is, so this is the thermal voltage of the transistor, which is typically 25 millivolts. This is the quiescent current on the transistor, and then added to that is the effective resistance on the emitter. So that's 4.7K in parallel with 1K in parallel with, this is beta AC, so that's FT of this 2N3904 is approximately 300, divided by the frequency that I'm looking at here, which is 14 megahertz. And then that's outside of 25 millivolts divided by 27 milliamps, which is the quiescent current. And then added to that, those two 47 ohm resistors in parallel, which is 23.5. So the final result is 4700 in parallel with 1000 in parallel with 523, which gives an effective input impedance of 320 ohms. So let's move on now to what the effective output of this amplifier should be. Now, what I have on the input is a 56 millivolt peak, effectively a 56 millivolt peak-to-peak signal coming in at 14 megahertz. So to calculate the output, this is kind of the path to go through. So T1's winding ratio is 24:7. So that means the impedance ratio between the secondary and the primary is 24 divided by 7 squared, which is about 11.755. Now the impedance that I'm presenting to the collector, so the impedance I'm presenting to the collector will be the value of this resistor times that turns ratio squared. So if we move back here, that means there's an effective 505 ohms of impedance at the collector. And so to figure out the gain in this configuration, it's the collector resistance divided by the emitter resistance, which is 505 divided by 23.5. So that's effectively a gain of 21.5. Now, there's that 56 millivolt peak-to-peak signal being presented to the base. So I multiply the gain of 21.5 multiplied by the peak-to-peak voltage presented at the base, and that gives me 1.2 volts peak-to-peak. Now that's at the collector. So if I want to figure out the output after the transformer, I then have to multiply that 1.2 volts peak-to-peak by the inverse of the turns ratio, so 7 divided by 24. And the result of which, well, you can't actually see that. Let me move over it a little bit. So the result of which is a 351 millivolt peak-to-peak signal. So please, I'm definitely not an expert in any of this stuff. If any of my math is wrong, it'll help me for you to point it out. So if anything here's wrong, please do point it out. I won't be embarrassed at all, or at least I won't be much embarrassed. So anyway, let's just see what that output looks like on the oscilloscope. So just panning up to the oscilloscope. Let me zoom in a little bit so you can see that. And what you can see here is, so we've got that 14 megahertz signal coming in here at a 332 millivolt peak-to-peak. So that's pretty close to the estimated or calculated value. So kind of pretty happy with that. What I'll do now is move on to the second stage, and that consists of the 2SC 5706. Let me just pan down to the board so you can see where it all goes. So the second stage, let me get the probe out of the way here. So the second stage takes up this portion right here, and then following from that is the first of the binocular toroids here, and then you have a pair of 22 ohm resistors that set the impedance presented to the 2SC 5706, and then you have the MOSFETs after that, and so on and so forth. So what I'll do is I'll go and put all this circuitry in, including the binocular toroid, and then we'll come back and probe some voltages. Okay, so this is just a quick progress update. As you can see, I've got the binocular toroid in place here, or binocular core rather, and this actually forms a splitter function on the collector output of the 2SC 5706, which I've got in place here. together with its associated circuitry. And then on the output side of the binocular core, I have this pair of 220 ohm resistors, and they're effectively in parallel. So you've got 220 ohm resistors here in parallel. So that actually presents 110 ohms to here. And then there is a 1 to 4 relationship presented to the collector of the 2SC5706. So you effectively have 440 ohms presented here from these two 220 ohm. So anyway, let's have a look at the output. Again, I'm injecting the same signal, and there is the output, and that's effectively at the gate of the gate of where the MOSFETs are. So you can see the phase and anti-phase signals here at 14 megahertz. So all in order. There is a little bit of an interesting imbalance between the two. So one of them is 1.43 volts and one of them is 1.36 volts. I did swap the oscilloscope leads around to see if there was something in the oscilloscope leads, but it wasn't. That's actually just a bit of an imbalance there. Not quite sure what that is. But that's basically the build up to the gates of the. Let me just pan over to over here for a bit. Let's go back to the circuit here. Bear with me while I get there. So there we are there. Let's just. So basically, that's probing this point here and this point here. So the next step is to get the BS170s installed, and then obviously it's got a few other little bits and pieces. This is the power supply there. So this is an RFC between the midpoint of the other binocular core that supplies a 12 volt the 12 volts power. And then finally we have the low pass filter on the other side. Sorry, you can't actually see that. Let me just pan over. So here's the low pass filter on the other side there. So I'll get that installed. Like I said, I've got a spot in there for a heat sink that I'm gonna put on. I've drilled a hole between those two BS170s, and I'm gonna bend them over and lay them flat and create a little heat sink for them. So that's coming right up. So just another quick update. I've installed the other binocular core, and as you can see, I've got these two BS170s sort of facing away from each other but bent back towards each other, and then I'll use this screw here together with this rather crude heatsink, and I'll put that on top of there like that, and I'll probably put either a sill pad or some heatsink compound between the BS170s and the heatsink itself. Okay, so I'll go and install that on there. I've got a few more things to install here. Here's the RFC which goes here. It's a smaller binocular core. There's a 0.1 microfarad cap there, and then just sort of panning up. This is where the low pass filter goes, and then I'll be pretty much done. So anyway, this is just a quick update. I'll come back when I've installed all those components. Okay, so here's the finished product. Here's the heat sink here, and those two BS170s are underneath it with some heatsink compound. Here's the low pass filter right here and here. And then, so let's just see what we'll get with this. So around about 4 watts. And unlike before, it's starting to sink now, but unlike before, it's a lot more stable in the output. Before it started to shrink almost straight away. Now, I'm sending this, well, let's just have a look at the waveform. Bear with me, I just got to move this around a little bit. So here's the output, around about 33.8 volts, peak to peak. A little bit less than I'd hoped for. I was hoping for around about 5 watts. And this is driving at, let me just zoom over to the SIG-Gen here. So that's driving it with 0.5 volt peak to peak on the input, which is a fairly heavy amount of drive as well. So anyway, that's a wrap for this video. I think it's an interesting. I'll probably keep playing around with the various values of the resistors on the emitter to see if I can eke out some more gain. But we'll see. This has been a bit of fun. Hope you enjoyed it, and I'll include links below to the kicad circuit and so on and so forth as usual. So if you want to try and repeat this, be my guest. That's a wrap for now.